Here we have a classic diels-alder reaction, and we all know by now perhaps that in a diels-alder reaction we actually need to draw three curved arrows. And those three curved arrows pertain to the double bonds that are present in this conjugated diene. We'll highlight them in red. And then also the double bond here in the dienophile. So three curved arrows, again, need to be drawn, so we're going to go ahead and try to do that. We'll take this double bond in the diene and we'll move it to this position here. And that's actually going to end up forming a new double bond right there in between those vertical carbons. Simultaneously, because this is a one-step concerted mechanism, this pi bond will reach out, so to speak, and attack this carbon right here. And then finally, the third curved arrow will be this pi bond reaching out and attacking that carbon right there. And so what we're going to try to do is stitch this together into one cohesive molecule. So we'll draw the former diene, and recall that we're going to have a new double bond placed between the vertical carbons, so right here. Then, and we might begin to color code things just to keep track, this carbon right here, which we might color in blue, is going to be bonded to this carbon over here, which will also be in blue. So we'll draw a bond connecting those two carbons together. And then we have a bond that is coming down here. And then we'll do pink here. So this carbon right here, which was right there, is going to be connected to that carbon of the former diene. So we'll put that in pink here. And then these will be joined together. Now what's a little bit tricky is we have to remember that between the blue carbon here and the pink carbon there was this extra carbon. Maybe we'll color that in purple. So this carbon right here we haven't yet drawn. And so what that's going to look like is actually a bit of a bridge here. So between the blue, there's going to be a purple carbon right there, which then goes on to bond to that pink carbon. So there's your little bridge that we said previously would form. And then we have to show some stereochemistry. The question notes that for the chirality centers with deuterium and these carbonyl groups, we have to specify the stereochemistry. Now, one thing to notice is that the carbonyl groups originally present on the dienophile are in a cis orientation. And cis, recall, just means that they were on the same side of the double bond. And now if those groups originally were present in a cis orientation, that means they have to be present in a cis orientation in the product as well. So what that means is those carbonyl groups are going to end up being pointed downward. And by pointing them downward, we would be showing that they are still indeed cis on the new ring that is formed. So just make sure that you point those groups in sort of a downward orientation. We're using the dashed bond to indicate downward. And then these deuteriums, they were also in a cis configuration, so they'll be pointing on the same side of the ring together as well. So we'll make those on a wedged bond to show us that they're projecting outward. So it might look something like that. So that would indeed be the correct answer with the correct stereochemistry. For those who are minoring in art, you may also choose to draw the molecule in this orientation, so we can kind of understand why this is equivalent. And we can see that if we kind of color code things accordingly. So here's that purple carbon that served as the sort of bridge right there. The pink carbon would be the carbon located down here. And then we have the blue carbon, which would be this carbon right here. So you can see that that bridge is still formed. We can see that the deuteriums are still on the wedges, and then those carbonyl groups are projecting downward, just like we drew it. So this is an equivalent way of drawing it. It's a little fancier, frankly, to draw it that way. Your homework system should also tolerate the way in which we drew it as well.